In the last video, we talked about simple rational exponents. These exponents were used to help make a larger number simpler to work with. We have found that rational numbers with a numerator of 1 will give us the root of our base number according to the denominator. For example, if we had a denominator of 2 in our rational exponent, our base would yield its second root. If we had a 5 in our denominator, our base would yield its fifth root. Let's now extend our work with exponents to include a number greater than 1 in our numerator. Say we have 9 to the 3/2 power. The easiest thing to do is to remember that we are working with exponents, and remember to treat the rational number exactly like an exponent. But at the same time, remember that we can manipulate rational exponents in the same way that we can manipulate rational numbers. We can factor out the numerator from our rational number. Thus, the 3/2 becomes a 3 times 1/2. So now we have 9 to the 3 times 1/2, or 9 to the 1/2 times 3. In other words, we now have two parts to our exponent, a whole number and a rational number. Using the whole number part first will act just like any other exponent. Using the rational number part first will work in the same way that we have explored in the last lesson. Remember our commutative property of multiplication, which says that A times B equals B times A. It doesn't matter whether we use the 3 or the 1/2 exponent part on our base first. But in my experience, making our number smaller, if applicable, as we shall see in an example, before making it larger is usually preferable. First, I'm going to use the 1/2 part of the exponent to the base, giving us 3 squared to the 1/2 times 3 power. This equals 3 cubed. At this point, we have done everything we did in our previous lesson. We took advantage of our base's root to cancel out the 1/2 power, and now we are left with 3 cubed, which we know is 27. It may take a few practice trials before you memorize which component of the rational exponent does what. Just remember, factor out the numerator. This leaves you with a fraction with a 1 in the numerator. That fraction in the exponent is meant to bring out the root of our base. One final statement needs to be made. Every non-negative number has a root, but it's not always prudent and sometimes impossible to calculate that root. Most roots in our number system are actually irrational numbers, which we have found to be quite difficult to work with. For example, see if you can find the square root of 2, or simply put, what two numbers multiplied together equals 2. I said this to say that sometimes it's better just to leave the simplified exponent as is, such as 2 to the 1/3 power. Trust me, you don't want to find this number right now, not at the current skill level of this math video. Let's rewrite our definition from the previous video. Definition of b to the m over n power. For all b greater than or equal to 0, and all real numbers m and n, b to the m over n power is equal to b to the 1 over n power to the m power, which is also equal to b to the m power to the 1 over n power. This states that as long as our base b is non-negative, if our base is raised to a rational power, we apply the distributive property of multiplication and factor out the numerator, and either simplify the exponent or take the root first. Let's work a few examples. Number 1, 36 to the 3 over 2 power. First, we recognize our root. 6 squared to the 3 over 2 power. Factoring our exponent gives us 6 squared to the 1/2 times 3 power. Using the 1/2 portion of our exponent, we simplify our exponent, leaving us with 6 cubed, which equals 216. Number 2, 7 to the negative 2 power raised to the 6 over 4 power. We can do one of two things first. We can either use the power rule and multiply our exponents together, or we can notice that our exponent can be simplified. We'll simplify first. We should always try to make our expression as simple as possible before moving on to the next step in algebra. Let's simplify to 7 to the negative 2 power to the 3 over 2 power. Now we'll work the inner negative exponent. 1 over 7 squared to the 3 over 2 power. Using our power rule and letting our 2's cancel out, we are left with 1 over 7 cubed, which equals 1 over 343. Number 3, 3 to the 3 over 2 power. First thing we'll do is factor our exponent, giving us 3 to the 3 times 1/2 power. Now notice that we don't know the square root of 3, and at our current level of mathematics, it'll be impossible without the aid of a calculator. Remember that simplifying doesn't always mean we're going to get a pure perfect looking number. So for now, we'll just apply the third power to our base, leaving us with 27 to the 1/2 power. Number 4, 2 cubed divided by 3 squared raised to the 3 over 2 power. We now have a bit more complicated expression. Let's simply go one step at a time. First, we'll use the power rule and multiply our exponents together, giving us 2 to the 3 times 3 over 2 divided by 3 to the 2 times 3 over 2 power. We notice that the exponent and the denominator of our expression will cancel out. So let's do that next, giving us 2 to the 3 times 3 over 2 power divided by 3 cubed. Now, the numerator is harder. So let's break the exponent down. We have 2 to the 3 times 3 times 1/2 power divided by 3 cubed, which simplifies to 2 to the 9 times 1/2 power divided by 27, which equals 512 to the 1/2 power divided by 27. This is as far as we can go. We can simplify a bit more, but we have yet to learn the properties of roots. Sometimes we will get complicated answers like this until we can learn the mathematics to continue. Number 5, 8 over 27 to the negative 2 over 3 power. Final example. We first take our inverse, 27 over 8 to the 2 over 3 power. We now recognize our roots, 3 cubed over 2 cubed to the 2 over 3 power. Finally, we factor and simplify. 3 to the 3 times 2 times 1 over 3 divided by 2 to the 3 times 2 times 1 over 3, which equals 3 squared over 2 squared, which becomes 9 over 4. These last two lessons was an example of how sometimes exponents may become rational. In the next lesson, we'll learn a basic symbology used to express these rational exponents, and we'll learn the properties of working with them just as we have with exponents.